Okay, I just wanted to make this screencast as there were a few questions towards the end of the lesson about how to, or what the best method to solve some of these conditional probability questions, and especially the sort of the theoretical ones, which are, I guess, textbook in style. Nevertheless, we still need to get our heads around them and understand and use a method that works. So what I was suggesting is that we use Karnaugh tables. I know that formula was chucked around. I'm not a big fan of it. I don't believe in remembering formulas that are not particularly useful. I think you need to save up your memory space for things that are useful. So if we go back to question 4, and this is question 4, and we're in exercise 11A, aren't we, on page 322. So I'll just spend a bit of time going over some of these and how I suggest we logically proceed through this section of work. So for events A and B, we're looking at 4A. The probability of A is 0.7. If you've got the question in front of you, it's going to be helpful. The Karnaugh table would set it up like so. And I think if you get used to this method, then it will work for all these questions, and that's obviously a nice thing if you can get a method that works for every question. Right, so that's 1 there. We know that's coming to 1, and we don't need to always fill out these tables completely. Now, probability of A is 0.7, so we put in 0.7 here because that's the probability of A column there, and probability of A intersection B is 0.4, and we want the probability that B happens given that A's happened. Well, given that A's happened, this is now our sample space here. That's our sample space, so that goes underneath. That goes underneath in the fraction. And what's the probability that B occurs, which is there, given that A has occurred? So our sample space is 0.7, so the probability of B given A, for me, is 0.4 over 0.7, which simplifies to 4/7. Okay, so that's for A. Now how about for B? Now for B, I'm just going to go the same way. I'm going to get the table together, B and B dash, and off we go with our noughts and crosses table again. We need a total down here. That's my 1 right there. And right, so let's start filling some stuff in. Probability of B is 0.5, so in this case we're going there. Now the probability of A given B, now that's this slot here. The probability of A given B, so 0.5 is my sample space, so I reckon I'm going back down here. Probability of B, probability of A given B is 0.6. Probability of A given B is equal to 0.6. Now this is therefore my sample space here. That's my SS. So what that means is my question mark over 0.5 has to equal 0.6. This is what I want in here. So my question mark is equal to 0.5 times 0.6, or 0.3. So in here goes, not a question mark anymore, 0.3. And so the probability that A intersecting B is 0.3. So we've got that sorted out now. So if we look at it like that, and we're really focusing in on the sample space and trying to figure out our problems that way. So let's again go with C now, and this is, I think, where we got to in the lesson. Got to a bit of a stalemate here, so let's make sure we've got this together. So this is our 1 here. Right, what's the information? Probability of A intersection B is 0.3, so that's in there. Now the probability of A given B is 0.44. So A given B. So what I want to know, I don't know what this is. That's going to be useful, but I know that 0.3 of it, because that's my sample space, probability of A given B. So this is probability of A given B is 0.44. So that's that bit of that is equal to 0.44. So my sample space, again, is the question mark, so it's 0.3 over the question mark is equal to 0.44. So that my question mark, in this case, is equal to 0.3 over 0.44, which is equal to 30 over 44, which is equal to 15 over 22. So my 15 over 22, that amount goes in there, and that's my probability of B, and that's the answer. That's what we're after. So hopefully, I mean, we're using logic here, and Karnaugh tables, I think, are great logical tools, and that's and that hopefully is helpful. So let's go to question 5. I think question 5 is even more obvious how that we're going to use it. Still talking about A's and B's, so let's get our A's and B's in place here. Off we go. Beautiful. Excellent. Right. The orange one goes in there. Okay. Probability of A is 0.5. Okay. Probability of B is 0.4. Good. Probability of A union B is 0.7. That's those three squares, or 1 minus that one. So if probability of A union B is 0.7, then this square, the A intersection B intersection, sorry, the A complement B complement intersection will be 0.3. This plus this plus this is 1.7. So find probability of A. Well, I can fill out all my squares now. They're my givens. Now it's 0.6, it's 0.5, it's 0.2, it's 0.2, it's 0.3. Now I reckon I'm home. Look at this. So the probability of A intersection B, probability of A intersection B, that's just that square there. So that is there, which is 0.2. Probability of A given B. Alright, now I reckon these are easy to go as well, because now my sample space given B is 0.4. So 0.4 is my sample space. What's the probability of A given that we're in their sample space? It's 0.2. There's the A bit of it. There's the A complement bit of it. 0.2 over 0.4, that's a half. Probability of B given A. Now we're in, this is my sample space, 0.5. And the probability, the A bit of that is 0.2. So that's 2/5, or 0.4. And there's question 5 done. See if you can use Karnaugh tables now to get through the rest of exercise, what's that, 11A. Because tomorrow, Thursday, I really need you to finish this off, because on Thursday we need to be getting on with independent events, which I am going to add a page for here. Put my title in, and if you could take down a single note on this, independent events, and often we're asked to establish that events are independent. Now for independent events, what we're going to say is that, and it's just when A and B are independent events. What that means is the outcome of one does not affect the probability of the other. So when A and B are independent events, what we get is simply that the probability of A given B will just equal the probability of A, and vice versa. And perhaps more usefully, the probability of A intersection B is just equal to the product of the individual probabilities. Probability of A times the probability of B. So that's really where we'll be focusing our work. And if you're asked to prove that two events are independent, go and find the individual probabilities and show that it's the same as the probability of the intersection of the two events. Okay, so that's really all you need. I need you to just take those notes down. Really need you to get to the end of exercise, the work requirements on 11A, and then in class on Thursday we can work on exercise 11B. I'll see you then.